In this video we're going to examine a process of mixing which results in a mixing condensation level, or an MCL, and produces stratocumulus cloud. The mixing condensation level, or MCL, is the lowest level at which saturation occurs due to mechanical mixing, so mixing produced by the wind flow. Here we have a schematic Sc log P aerological diagram where there's mixing through a depth indicated by the solid line, which is the top of the mixed layer. If we don't add heat or water vapor during the mixing process, then parcels of air at each level will conserve their value of potential temperature and mixing ratio, and the net result will be to produce a temperature and dew point profile which match a mixed dry adiabat and a mixed mixing ratio isopleth. If a saturation point, or if these two lines cross below the height of the mixed layer, then we'll have a mixing condensation level, and above that the profile will be a saturated adiabat. So the way in which this is done is to use the equal areas method. So take the depth of the mixed layer and find the mixing ratio line which produces equal areas to the left and to the right of that. Likewise, do the same thing for the temperature profile and the mixed dry adiabat. And if the two cross below the depth of the mixed layer, then you have the mixing condensation level, and between that and the top of the layer, which now will form a mixing inversion, will be stratocumulus cloud. So there's our two lines meeting at the mixing condensation level. Let's try this out. Stop the video now and plot the trace as shown. Assume the depth of the mixed layer is equal to 200 hectopascals and calculate the mixing condensation level by this equal areas method, that is, choosing a value of potential temperature that gives you equal areas with the temperature profile and a mixing ratio isopleth that gives you equal areas with a dew point profile. Once you've done that, examine your results and switch the video back on. So how did you go? Hopefully you got something like this. So in pencil we can see the temperature and the dew point profile, the height of the mixed layer is indicated, the mean potential temperature is 26 degrees, that's our temperature profile, the mean mixing ratio isopleth is about 7.7 grams per kilogram, and it gives you a mixing condensation level of about 780 hectopascals. So what we see in practice is the result. Typically you don't observe in a sonde the pre-mixed environment, and you don't have the temporal resolution in radiosondes to see that process going on. What you'll see is what's shown in the schematic, where there will be a saturated region or a near saturated region characterized by a small dew point depression somewhere between above the surface, and an inversion which results from this mixing, but also other things like subsidence. We'll talk about that later in a later lecture. So the mixing depth is determined by an inversion, also by the wind profile and any air mass change. As a real example, we can see in the bottom sonde from Sydney Airport that most of the wind flow is northwesterly, but there's a shallow southeasterly wind there of 5 knots, which is possibly a weak sea breeze. This is an 05 UTC trace, and you can see that that produces an increase in the moisture in the lowest parts of the trace. Then you can see a weak temperature inversion and a weak inversion in the moisture as well, which is likely associated with this weak mixing that's occurring. Let's look at some examples of stratocumulus environments. So on the left we have a mean sea level pressure chart, and you can see over Melbourne that there's a broad southeast to southerly flow. You can see that there's on the right hand side the Sc log P for 23 UTC on the 8th and 17 UTC on the 8th. You can see there's been a change in that 6-hour period. The dew point depression has increased and the entire profile has moved to the right, so there has been warming but also an increase in the moisture, even though the dew point depression has increased. The blue profile from 17 UTC corresponds to the 17 UTC METAR for Melbourne Airport. You can see there where, with a wind direction of 170 at 9 knots, there was 7 octaves of stratocumulus at 3,100 feet, or 3,100 feet. And if we do our mixing game on the profile, you get a cloud base of about 3,200 feet, so they're really close. Then over time the environment changes, and you can see the dew point depression, as I said before, at 23 UTC has increased. The whole thing's moved to the right, and we now only have 5 octaves of stratocu, but at a slightly lower base. And you can probably see that just looking at the dew point depression. The base is a little lower at 2,700 feet. As a general rule, the closer together the temperature and the dew point lines are, in other words, the smaller the dew point depression, the more likely it is that you have broken cloud. And the further apart, the more likely it is that you only have, say, scattered, or maybe even few. Here's an example from Hobart, and on the left you can see an infrared satellite image, and most of Tasmania is covered in a light shade of grey, indicative of low cloud. Here we have 2 profiles on the right that are separated by 12 hours, 11 UTC on the 8th, and the following morning at 23 UTC. You can see there's been quite a dramatic change. At 11Z, there's a very large depth of atmosphere where the dew point depression is essentially 0. And then on the 23 UTC on the 8th, you can see that that dew point depression has increased a little bit. The whole thing's moved to the right, so conditions are slightly drier and cooler, and the cloud base, or rather the cloud top, has decreased. The cloud base is a little higher. And so if we look at the observations, at 11Z you can see that there's 7 octaves of stratocumulus at 5,000 feet. Certainly it looks like a broken to overcast environment from both the satellite image and the trace due to the small dew point depression. But there's also 4 octaves of stratus at 1,800 feet. And that's no surprise as well that there's a couple of decks of cloud potentially through the wet bulb process, or just that it's a very saturated environment. Whereas by 23 UTC there's overcast, it's 8 octaves of stratocumulus at 3,500 feet, so it sits somewhere in between. Whereas previously we had 2 decks of cloud, which made the cloud very deep. Now we have only 1 deck of cloud, and it's shallower. The mixing condensation level in classic stratocumulus. So stratocumulus is formed by turbulent mixing and cooling of moist low-level air underneath a stable layer. And that stable layer is, of course, known as an inversion. And so you must get a mixing condensation level below the inversion height. So do the mixing calculations, and if the MCL is below the inversion, then you're going to get the formation of stratocumulus. The vertical extent of cloud can be determined by height of the inversion. So if it's particularly deep, then you're likely to have broad areas, availability of moisture, and the entrainment of drier air. Stratocumulus can be thick enough to produce drizzle, and it mostly appears in layers and broken valleys. So if you think back to the Tasmania example, there was a large area covered in a sheet or layer of broken stratocumulus. At Sydney Airport, they've come up with some so-called forecasting rules for the formation of stratocumulus. Firstly, you want a subsidence inversion. We'll talk more about those in a lesson on inversions, but the inversion acts as the top of a mixed layer. And ideally this is below freezing level. Typically stratocumulus consists of warm cloud, that is liquid water drops rather than any ice. You want a deep airstream with onshore component, and ideally up to the inversion level. And the comment about max frictional convergence simply says that if you've got a strong onshore flow, that flow decelerates as it hits the shore because friction is larger, and that provides you with some convergence. You want a turbulent wind or convection below the inversion. So stratocumulus can form either from mechanical turbulence, and that depends upon friction and wind strength and direction, mixing the air up, but also if you have convection below the inversion and the stratocumulus hits that inversion and spreads out. And so if the mixed condensation level is below the inversion, SC will form. Finally, how does stratocumulus dissipate? Well, it dissipates faster when you have a shallow layer between the mixing condensation level and inversion. In other words, the thinner the cloud, the easier it is to get rid of. and also if there's going to be a change in synoptic conditions which decreases the moisture supply and therefore the mixing. So the wind might shift from moist advection to advection of drier air, and that will help mix out the stratocumulus. If there's an inversion present with stratocumulus underneath, then heating will raise the mixing condensation level. That is, it will change the value of potential temperature, which represents the equal area method, and that will lift the MCL. So the cloud thins with time. Likewise, if there's a high ridging in, this results in enhanced subsidence. Again, we'll talk about this later. And so the inversion associated with that lowers, and it thins out the cloud. And so eventually the cloud will begin to clear. And so you will see a movement over time, which you'll have to take into account of in your forecasts, from broken to scattered to few, and then finally to CAV OK. Cloud and visibility OK, which means the visibility is 10 kilometres or greater, and you have no broken cloud below 5,000 feet. Now the time over which this occurs will depend upon the maximum temperature. For particularly hot days, you'll quickly erode, thin and get rid of the stratocumulus, and on cooler days you may not see the stratocumulus disappear at all. Here's another exercise. Again, plot the following trace on a skew-T log P and mix the lowest 3,000 feet, that is to 900 hectopascals. Does stratocumulus form? At what base and what top? Stop the video now, plot this trace and answer the questions. So how did you go? You can see why we might specify 900 hectopascals as the depth of our, or the top of our mixing layer, by looking at the wind profile. You can see how the winds above 900 hectopascals shift from easterly to westerly. And here's what it looks like. You can see there's a very strong inversion. Rapid warming with height and rapid drying with height. And you can see that there's a well-mixed layer in both the mixing ratio, both in the dew point, resulting in a mean mixing ratio line, and in the temperature, as indicated by the dry adiabat. And when you do this, you get a top of about 900 hectopascals, 3,500 feet, and a base of 915 hectopascals, or about 2,800 feet. So the deck of stratocumulus cloud is thin in this case.